Okay, so yesterday we looked at circular motion. So there's still one special type of motion we have to look at. That's called simple harmonic motion, or just sometimes SHM for short. Yeah. Now, yesterday we were talking about springs and Hooke's law, and you can imagine with your spring, if you gave it a hit, it would start to move up and down like this. The spring, yeah. So like, I don't have anything like that. I should bring something with me. You know, if you have a spring and you pull it and you let go, it's hanging there. Then if you just maybe flick it, it will go, you know, start to move like this, start to wobble. So let's have a look at the graph. So let's imagine I hit the spring here. So it goes faster, 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 then it slows down, and then it goes back down. Then it goes faster, 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 then it slows down and goes back up, goes up and down like this. If I was to draw its graph, time and velocity, its graph would look like this. It would start really fast, then it would slow down when it's here, then it starts to go down. Yes, come in, must be young. Young, come on. You can step over? No, over, yes. Yes, yes, okay. Then when it goes down, it has a negative velocity. And then when it goes back up, starts getting faster again. I mean, the graph, I'm trying to say the graph looks like this. It keeps getting faster, slower, faster, slower, faster, slower, faster, slower, like this.
Down is lower.
Down, here? Yeah, that is negative. So yeah, it's going, it means it's going down. And then here, positive, means its speed is going up. So it's getting faster and slower. Yeah. I think that's all I want to say right about now about that. Okay, what's the reason for this? That's what I'll do. So why does it move like this? And the reason it moves like this is because in Hooke's law, you have this. But you know F is ma. Just think about what this means for the moment. I'll wait till you have it. What do you need? Pen? If you look here, imagine the ball is to the right here. So the x is positive or negative? Positive, yeah. What's the acceleration, positive or negative? No, it'd be negative because the minus here. See? This would be positive, 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 negative. So which way is the acceleration? To the left. So is it getting faster or slower? If something has negative acceleration, what's it doing? Getting slower. And it'll get slower and slower and slower until it stops. And then it'll go back the other way. And then when it's on the left, It's x, is it positive or negative? No, on the left, it's negative. And what about the acceleration? Positive. So that means it's accelerating back to the right. In other words, when the ball is to the right, it wants to go to the left. And when it's to the left, it wants to go to the right. So it ends up moving like this, back and forth. This is called simple harmonic motion. So we can say, we have simple harmonic motion if the acceleration, well, I'll write on the next line, equals a minus constant multiplied by position, displacement. So if you have this type of acceleration, then you will get this simple harmonic motion going back and forth. Simple harmonic motion is important in physics because many things move like this. Can you think of any examples where we have simple harmonic motion? Can you think of examples of motion like this? Pendulum, yeah. What else? Springs, yes. But really, what else?
The beat machine.
Yes, I'm sure there's some kind of beat machine. Which machine?
With you the piano.
Oh yeah, very good. That machine. Yes, that's right. That would be simple harmonic motion. You know the machine she's talking about? I think that machine is called a metronome. I think it's metronome. I know what you're talking about. It goes like this. Yeah. Anything else you can think of? Clock. Yeah. Pendulum. That's called. Yeah. And you know things like ocean wave. You know the ocean wave. The tide. The tide goes high, and then maybe in the evening the tide goes low. So during the day, it's going up, down, but really slowly. Yeah. So it's important, this simple harmonic motion. And just like with circular motion, you have some formulas. So let's have a look at the formulas. Now, first formula, I actually have it already there. But it is much more common to write this formula in this form. Yeah. Where this omega is squared is the constant I'm talking about. So why do we have two formulas here? Well, the reason is, this formula right here, this is only when we have Hooke's law, you know, when you have springs and strings and things like this. Whereas this formula is general. It's for any type of simple harmonic motion. But if you want to convert from here to here, you can just say omega equals square root k over m. So that's kind of like a formula as well. We'll call that 3. Okay, so before I give you more formulas, I better give you more terms and definitions. So we'll just have those 3 for the moment. But they really are just coming from Hooke's law from yesterday. Okay? So I'll just go to the side for the moment. Just a bit of terms. So this mass here is moving with simple harmonic motion. So that means it's moving to the left, and then it's moving to the right. It's going back and forth. Okay? This distance here, we call it A. And this distance here, we call it A. It's like the maximum it can move. Okay, so with Louise, your example with the metronome, the A will be this distance it can move, the maximum distance, okay? And with the pendulum, where it's swinging left and right, the A will be the distance it can move on either side at the bottom. So, does anyone, I don't know if anyone knows this word for what we call this A here. Amplitude. Yeah, amplitude, yeah. So this A is called amplitude. So here in my picture, the ball is moving to the right, and then it will move back to the left. This distance here, x, well, that's just the normal word from chapter, or week 1, displacement. Do you remember what big T is? The time. The time for one cycle. Remember this from yesterday? What do we call this? I think you said it there. Yeah, what is it?
Periodic time.
Periodic time. Or just a period. And do you remember what the frequency is? Sorry, remember what the F is? Frequency. Yeah, the number of cycles per second, yeah. And that omega, that's called still angular frequency, so we have this from yesterday as well. And there's another word here, I'm going to put it in green, and we'll look at it later. Phase difference, we haven't done that, we'll look at that later. So I just want to write down what all the letters mean. Okay, can I go back to the formulas? Yeah, okay. So we have these 3 formulas. Who remembers what this omega means from yesterday? What did the omega mean? Angular velocity. Remember? What's the unit? Radians per second. But if it's going left and right like this, then what could it mean here? Because there's no angle, it's just going in a straight line. So, what type of speed though? No, like any ideas? I'll give you it. So, let me give you an example here. Yesterday, we did circular motion. So we have this going around in a circle. Okay, and today we're doing this simple harmonic motion where it's going left and right. Now, if I just connect this here, and this is like on a train. So as the wheel turns to the left, what will happen to this? It goes to the left. And then when it's, I'll put it in a different colour, like for example when it's up here, alright, now I'm not drawing it very nicely, but you get the idea that when this moves around in the circle, this will move left and right. Like a train. You know what I mean by a train. You picture the train, the wheel moving, this going back and forth. In fact, the omega here and the omega here, they're the same. And the omega here, what you need to imagine is, if it was connected to a wheel, it would make the wheel turn at the whatever radians per second. Now that's not really important for us, but I'm just trying to show you that you can make a relationship between the two. The other example is, you know that machine you put your foot up and down on, and then you can sew your clothes? You know this? The sewing machine? But I don't actually know if it is a sewing machine or if it does something else. But anyways, you're doing something with your clothes and your foot is going up and down. Oh yeah, you're spinning. The wheel is spinning, isn't it? Yeah, so it's spinning wheel. So the wheel is spinning. So this is circular motion. But your foot that's moving up and down, that's simple harmonic motion. So I'm just saying that you can link the two together. Okay, they're not separate chapters. You know, you can think of them as being related. Okay, but it's just an idea. It's not so important, so don't worry about it. I'll just go back to the formulas now. So we have these three formulas. So let's get some more. So the next formula is if you want to know what the velocity is. So the velocity squared equals omega squared a squared minus x squared. The time is still 2 pi over omega. So what formula is this now for? The maximum velocity. So what I mean by this is the fastest it can go. Because you know it's going slow and then fast and slow and then fast. So this V max is the maximum it can travel. It's maximum speed. Yeah.
T equal to?
2 pi. You know pi? Yeah. And then A max, the maximum acceleration. And then the final formula this last formula, it can tell you the x if you know the time. But the reason there are two is because if the motion starts in the middle at t equals 0, then we use this formula. If the motion starts at the wall, or at the amplitude, at the beginning, then we use this formula. And you might say, hang on, what about if it doesn't start in the middle and if it doesn't start at the wall? What if it starts somewhere else? What about if it starts like somewhere here at the beginning? So this here is moving left and right, this here is moving left and right, this one here is moving left and right. So what do we use if it doesn't start in the middle? Well, this almost never happens in the exam. I think it's only happened once in the last 8 years.
Yeah, that's fine.
Yeah, you add an extra term in the formula. And that's the word I told you about earlier. That's called the phase difference. It lets you fix your formula if you don't start at the middle or at the end, if you start somewhere in between. Now these formulas aren't going to mean anything to you until I do some examples. So in a minute now I'll do some examples. Okay, can I do an example? Okay. Yeah. Okay, so here's my example. Louise, let's go with the one you picked now, the metronome. So we picture that this is going left and right, like this. So you give me the numbers. You tell me. Let me draw this again. We'll have it starting. We'll put it starting at the end, and then it will swing over to here. So it's going back and forth like this. Okay. So what would you say is the amplitude, the A? Remember, the A is the distance from the middle to the end.
Is that true?
No, what did you say? Yeah.
That's the natural.
Not well.
Constant.
It's a constant, like the natural length, but not the natural length. It's like the limit, the maximum it can move.
So actually, it's different for the yesterday.
Yes, different. What number do you want to pick for A? How big do you think this will be? You pick a number. Yeah. Roughly. I just mean like roughly. It's going back like this. 2 centimeters? What do you think?
I think maybe 2.
Yeah, maybe 2.
Too big.
Yeah, well, not too big. So we'll say 2 centimeters, okay? And let's say the time. How quickly will it take to go back and forth? What will be the time for 1?
1 second? Or 2?
Yeah, no, 1 second. 1 second seems fine. Yeah. So now what I want people to do for me now, I'll write down what I want you to calculate for me. So the first thing I want you to calculate is this omega constant. Hugo, you sound like you're dying over there. Are you doing okay?
Yeah.
Okay, so what do we get for omega? Do you know? Well, firstly, which formula do you think you need to use? Yeah, everybody have a look, but that's the one. Can you see which one to use for omega? Yeah, which one? What's the formula? Yeah, 2 pi over omega. So you could say that omega equals 2 pi over t if you switch them. Can you see that? Yeah. So here omega would equal 6.28 is the omega. Okay. The maximum velocity. Calculate this for me. Yes, calculator time now. So tell me what you get. Well, what formula are you using? Which one? A omega. That one, yes? Yeah. what do we get?
0.125.
0.125 meters per second. Now, my question to you, where will this be when it's going at its maximum speed? At the end? At the middle? At the end? Somewhere in between? Where will it be? Where do you think this maximum speed happens? Nope, sorry, at the middle. Because if you think about it, it'll slow, stop, and then go back. Faster, 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 fastest, slower, 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 stop. Faster, 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 fastest, slower, 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 stop. So right in the middle here is when it's going the fastest. Okay. It's important to know that. You might get that in the exam as a 1-mark question. You know, part 3 might be, for example, where does this happen? And the answer is in the middle. At the middle. Okay. Alright, part 4, I want you to tell me what the maximum acceleration is. Okay, what do we have for this? So the formula, which formula are you using? The omega squared. A, isn't that it? Yeah. So what did you get when you put the numbers in?
0.78.
And I should really put the minus in, but anyway, 0.789 meters per second squared. Now, my question to you is again, where do you think this acceleration is maximum? At the end this time, yeah. That happens at the end. Here. Here. Okay. Next one. Let's see. Which formula have we not used yet, really? We haven't used that one, number 4. Okay. Oh yeah, I know. So, it's getting a bit crowded, but can you see here in my picture, let me put it in on green. Here, you said this distance is 0.02. So let's say here is 0.01. So my question is, how fast is it moving when it's here? Now wait, before you start, should your answer be bigger or smaller than this? Smaller than this, because this is the fastest in the middle. And what's the speed here at the end, at this place? 0. So your answer should be somewhere between 0 and 0.125. If you got a number between the two, then maybe you got it right. So I tell you what the x is. I tell you that the x is 0.01. I would like the v, the speed. So tell me the speed now, please. I give you the x. So which formula do you need to use? Well, you need to use the formula with the v squared in it. Do you see which one? Yeah, what answer did you get, Saeed?
0.011.
Sounds believable. What did you get? Good. Did you get an answer? Oh no, what did you get?
0.109.
Sounds like someone has a zero too much.
Did you square it?
Sorry, no, maybe you said it. Did you say 0.011 or 0.11?
0.011.
Oh, okay.
Did you square it around?
Did you square root? Oh, well, I'll do it. So the formula is v squared equals omega squared a squared minus x squared. So v squared equals, what was the omega? Oh, there it is, 6.28 squared, 0.02 squared, minus 0.01 squared, and then I want the v, so I'll just do a big square root. And that comes out. Is that what you typed in? You want double? Oh, it is this one. Okay, alright, right. 0.10, 0.11 roughly meters per second. Yeah. Okay. So just like yesterday, we're really just using formulas, you know. It's just good to understand what's happening here with the motion. So we're going to have a look at some more graphs to do that, okay? Can I go down? Okay, so let's just go back to our spring, for example, here. So our spring is moving back and forth. So we'll say this is A and this is A here, and it's moving between this place and this place. So it's going back and forth, back and forth, back and forth. Okay, so let's look at some graphs here. First one is velocity and then time. So let's say it starts here in the middle. What do you think the velocity is? There's actually zero here. No, sorry, it's actually really fast here. Remember we said the middle is fastest. So it starts really fast. And let's say it's moving to the right. Is it getting faster or slower? Slower. Until it stops. Where does it stop? At the end here. And then what happens? Then it goes backwards. So anyways, I'm just saying that the graph for the velocity will look like this. What about if I did graph of x and time? So at the beginning, what's the x? Well, let me help you out here. I'm going to call this place here the origin, the starting point. So at the beginning, x is 0. Then what happens? Does the x get positive or negative? It gets positive if it goes to the right. So anyways, the graph would look, if I zoom out a bit, will go like this. And in fact, I know what this height is. Who can tell me what this height is?
A.
That's going to be A, because the biggest x can be is A. Now, let's do one more graph. Let's look at the acceleration. Do you remember from our chapter on time velocity time graphs? On the graph here, what represents the acceleration? It's the slope, remember? So here, the slope is 0. Here, the slope is negative. Here, well, sorry, that's still negative, negative, and then here, 0, and then here, positive, 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 here, 0, negative, negative. So the acceleration at the start is 0, and then here is 0, and then here is 0. So if I was to graph that, acceleration starts at 0, then does it go positive or negative? Negative. So it looks like this here. But that kind of makes sense, because if you think about the formula for acceleration is minus omega squared x. Now look at the graph for x and look at the graph for a. What's the only difference between them? It's just upside down. You see how this is upside down at this? Again, because of this formula, the minus here just flips it upside down. Okay, more interesting now is the energy graphs. So this is the graph for position, velocity and acceleration. Let's have a look at the energy graphs. Okay, so everybody, can you please keep this picture in your mind as I go down? Okay? Right. So let's look at kinetic energy and time. So at the beginning, would you say the kinetic energy is big, small, or 0? What do you think? What do you think? What? I don't know. At the beginning, it starts in the middle. It's high. Because at the middle, remember in the last question we said at the middle it's the fastest. Yeah? So, what's the formula for kinetic energy? A half mv squared. So if the v is really big, then the kinetic energy is really big. And if the v is 0, then the kinetic energy is 0. So the graph would look like this. It would start really big, then would go down to 0. Ah, that's too quick. Go down to 0. Try this again. Go down to 0. But it doesn't go negative. It can't be negative. It's just positive. So it goes down to 0 and then it goes back up. And then it goes back up. And so on. So this is what the graph of kinetic energy looks like. So you see these points here, this is when the kinetic energy is biggest. That is when it's at the end. No, totally wrong. That is when it's at the middle. This is when it's at the ends. Okay. Now just for a moment, do you remember potential energy? What was the formula for potential energy? mgh. Do you remember this formula? So if you put something at height, it has energy inside of it. Yeah? What about a spring? If I have a spring, and then I go like this, push it really, really tight, it has energy inside of it.
Yeah.
It's like I stored the energy inside of it, because then if I let go, the energy comes out. Yeah. So for a spring, its potential energy is not mgh. It's a different formula. Potential energy is a half k delta x squared. So the more you extend the string, the more energy you store inside of it. So you see, if the delta x is really big, then you have lots of energy inside of it. Now when you let go, all the energy turns into kinetic energy. Yeah? If you picture here, do you remember if you have the ball up and it's really high, its potential energy is really big. And then as it falls, what happens to the potential energy? It becomes zero. Where does this energy go? It goes into kinetic energy, which will now be very big. The same for the spring. If you pull the spring really, really far, it has lots of potential energy. And then when you let go and the spring snaps back, here the potential energy will be zero, but the kinetic energy now will be really, really big, because all of this gets changed into that. So anyway, this is a new formula. This is the potential energy for a spring. So you need this formula. Sometimes you don't know what the K is. Sometimes you only know what the omega is. But that's okay, because if I go back earlier, you can use this formula to change between K and omega. So if you don't know the K, you can find it from this formula if you know the omega and the mass. Okay. So let me do an example that uses this now maybe. Can I go down? Yeah. Okay, so let's have a look at an example. So, let's see. Okay, so I have here, hanging on the wall, a spring, and it's going up and down, and its frequency, we'll say it's going pretty fast. Frequency is 4 Hertz. So this means per second, how many times does it go up and down? 4 times. So that's pretty fast, isn't it? It's like 4 per second. So it's moving pretty fast. Okay, so first question. What is the T? Second question is what is the omega? Oh, I should tell you the mass as well. The mass is 0.1 kilogram. And then part 3 is what is the K. Alright, so the first part, what formula could we use to get this one here? T equals, or F equals 1 over T is how I think I wrote it when I gave it to you. What formula could I use to get the omega? I could say T equals 2 pi over omega. Now, what formula could I use to get the K? Omega equals root K over M. So I want to give you a minute to give me these 3 pieces of information here. Okay, so the first part, do you have a T for me? Yeah, the T is 0.25 seconds. Did you all get that? Or you're doing it now? I'll give you another minute. So I'll give you oh sorry, that's not what I want. Yeah, the T I want first. Yeah, and then the omega next then. Yeah, what is it? I'll give it to me as a decimal. 25.13. 25.13 radians a second. Okay. And then finally, by using this formula here, you can get the K out. Let's see. So just who's got the K actually? I just want to see. Do you have the K? From using this formula. You can get it. I'll give you a minute to get the K. You have it, Joe? Yeah. Is it the same?
63.
Okay. I'll do the last one here. So we have omega equals root K over M. So we have 25.13 equals root K over 0.1. So what should I do first here? Square, good, yeah, square. Yeah. Saeed, can you tell me what this number is when you square it? What do you get?
Uh, 631.51.
Okay, equals K over 0.1. So we just bring that up and we have our K. K equals 63.2, roughly. Do you remember what the unit for K is? We did it yesterday, the unit for K. Yeah, so this is newtons per meter. Okay, next part of the question. So if I just go up to the picture for the moment. This is moving up and down, up and down, up and down. So, let's say here, let's say the amplitude is 0.1. So when the spring is here, this, can you imagine, is become compressed? So there's energy stored inside of it. So my question is, what's the potential energy? The potential energy when the x is equal to the A, which is equal to 0.1 meters. So what's the potential energy then here? So you have to use the formula, and you can use it now that you have the K. Okay, do you have an answer for me? Potential energy is a half K x squared, or delta x squared. So that is 63.2 divided by 2 times 0.1 squared. What do you get? 0.316 joules. Or if you prefer, 316 millijoules. In the exam, they like you to draw the graph of the potential and the kinetic energy on the same graph. So, oh sorry, can I go down? It's okay? So, let's look at this here. Here's our graph. So here is the energy. And here's the time. So look, in red, that's kinetic energy, and then in blue, that would be potential energy, and then in green, that can be the total energy, the energy of the kinetic plus the potential. Alright, let's go back to our spring. So at the beginning, let's say it's going up and down. So let's say at the beginning the ball is all the way down. So what would happen next? It will start to go up. Yeah? If the ball is all the way down, is it going very fast, very slow, or zero? What's the situation? Zero. And then what happens when you let go? When you let go, it starts going faster, and then stop, and then back down. So at the beginning, is the kinetic energy big or small? Kinetic energy. It's 0. So in red, here. And then what happens when time goes by? Kinetic energy gets really big. Yeah. And you know what? I'm going to change this actually. Rather than having it as time, I'll have it as x. So when x is 0, sorry, I'm getting myself confused. Sorry. X. So when I put it down really big, the x, is it 0, not 0? I mean, what's the value for x when I haven't pulled down all the way? In my example it was 0.1, but just what's the letter? It's A. If you pull it all the way down, the x is equal to A. And then as you let go, the x gets smaller, then it gets 0, then it goes negative, then it goes minus A, then it goes down to 0 again, then it goes positive, and then it's A. So at the beginning, this is when the t is 0 at the beginning, x is A, and the kinetic energy we said is 0. Now what's happening to the x in the next 1 second, the next 2 seconds? What's happening? Is the x getting bigger or smaller? It's getting smaller. And what's happening to the kinetic energy? Is it getting bigger or smaller? Bigger because it's getting faster. So this red line here, as the x gets smaller, the kinetic energy gets bigger. And then when the x is 0, that's when you have the most kinetic energy, when it's the fastest at the middle. Then it will go negative, and then all the way back at the other side, at minus A, no kinetic energy. Now, potential energy. At the beginning, when x is A, is there a lot, a little potential energy? What's the story for potential? There's a lot. Why? Yeah, it's when the string is fully pulled, it has lots of potential energy inside of it. And when you let go, it moves quickly. So here the potential energy is very big. Then what happens as the spring gets smaller? What happens to the potential energy? It decreases. When this gets smaller, the potential energy decreases. And then at the middle it's 0. And then it goes back up. Now finally, maybe someone can tell me, if I add the kinetic plus the potential to get the total energy, what type of graph would that look like? Yeah, where should I draw it? Huh? In between, like somewhere here? Nope. Any ideas? Up the top here. Because if you think about it here, there's no potential energy, all kinetic energy, so the total energy is here. Now if I move a bit to the right, I have less kinetic energy, but I have a little more potential energy, so when I add them together it still stays up the top. Anyway, this should not surprise you. Because if you remember from energy, we said energy cannot be created or destroyed. The energy stays the same. So this total energy must be a constant. And on the graph that looks like this green straight line here. Now the reason I'm spending so much time on this graph is because they love this in the exam. That's the love part. It's such a common question in the exam. They would say, graph the energy graph for this problem. It always looks like this. It's always like this. I see this in the exam many, many times. So it's really, it's a graph. Of all the graphs today, it's the graph you must know perfectly. Okay? Of all the graphs, this is the most important one. So this is very important graph. Now let me just see if there's any other words I have to give you, and I'll let you try these. Oh yes, one more weird thing to do with you, then I'll let you try some. Make sure you draw this very clearly in your notebook, okay? Can I go down? Oh no, you need to draw it still. Maybe you can copy it, Saeed, from someone else then. Yeah. Okay. Back to our spring here, hanging on the wall. So this is going up and down with a time t. Now here's my question. Don't answer it without thinking. Think first, then answer it, okay? Imagine this wall is, this ceiling is not a ceiling. Instead, imagine like I hold this here. Here's the spring, and I pull it down. I let go, and then what happens? It goes like this. Okay. Now imagine now I can move this. So now I start to do this. So my question is, what happens to this t if I start to move this? If I make a simple harmonic motion at the top here. So if I go like this, up, down, fast, slow, like this. What happens to the t down here? Think first, and then give me your answer. Okay. Who wants to give an answer? So, do you feel like you have an idea?
It goes with that moves. The word moves up, and when it moves up, it goes up.
Yeah, so do you think this gets bigger, smaller, stays the same? What do you think happens to the number t? So like for example, if this takes 2 seconds to go up and down, and let's imagine I move this really fast, simple harmonic motion, what do you think happens to this t?
Goes up.
Okay, so you're going to say increase. Okay. Saeed, what do you think?
The same.
Stays the same? Okay. Louise, any opinion? Okay, so we have 2 for increase, 1 for stay the same. Who?
Decrease.
Yeah, why not? Decrease. Just in case. Jan, which do you think? Don't know? Okay, so don't know, that's a 1. And Ugo?
Decrease.
Which one?
Decrease.
Decrease. Correct answer? This one. Stays the same. It seems very strange that if I move this, it doesn't change the time here. It has no effect on the time. This seems really, really strange, doesn't it? You feel like if I'm moving this really, really fast, it should maybe make this move faster. It should make this maybe smaller. Or maybe bigger. It should change it. In fact, it doesn't change it. It's quite strange, isn't it? Right? So, what does change though? Something does change. What changes is the amplitude. If I start to shake this, what will happen with the spring is it will start to move more. The time stays the same, it just moves more up and down. So here, this here is called, hang on, get the correct term, I think it's forced oscillation, let's see. Yeah, this here is called forced oscillation. So what this means is you're putting an extra force into it. So please note, all that changes is the A, which I think is quite amazing. The T and F and K and omega, they're still the same. It's only the A that changes.
So actually, if I move the top, and the ball is same.
What do you mean same? The time is the same. Yeah, yeah.
Actually, if I move the very fast, it also is same the time.
Yep. Amazing, right?
Yeah.
Yeah. Same like with your metronome. You know your metronome's going left, right, left, right, left, right. And what did you say the time was? I think you said 1 second. So it goes like click, click, click.
Yeah.
If I take the metronome and I shake it like this, it still will go 1 click per second. The only difference is the handle will swing more, but it will still be 1 click per second. Okay. Now, why is this important? Well, there's actually some other feature here. Let me zoom out here. Actually, can I go down, or do you need a minute to draw this? Yeah. Okay. Is this okay? Okay. So in your mind, you have this here which moves with, I'll say, omega. So here's our spring moving up and down. And then here's the person here. And they're moving their hand up and down. And let's say they moves with omega 2. I'll call this omega 1. How can we calculate omega? It's using here T2 would equal 2 pi over omega 2, and T1 equals 2 pi over omega 1. So if you know what the T is, you can easily get the omega. Okay? So my question is, next, if he moves this slower than this ball here, will the amplitude get bigger or smaller? So we have 3 things here. We can say that the the T2 is smaller than T1, T1 equals T2 equals T1, and T2 is bigger than T1. So if he moves this slower than the ball down here, does that mean his time is bigger or smaller than this ball's? If he's moving his hand slowly?
Bigger.
Bigger, because it takes longer to do one movement of his hand. Look, if he moves his hand slowly, his time is big. So that actually puts him here, okay? Okay, so if his hand is moving slower, then the change in A is small, which makes sense, doesn't it? If he's moving his hand slowly, the amplitude doesn't change much here. Now what about this? He moves his hand really fast. So his time is really small because he moves his hand really quick. Does this make the amplitude here bigger or smaller? What do you think? Oh, sorry, I mean to say, does the amplitude change a lot or little? Does the A change a lot or little? What do you think? If he moves his hand really fast? Think a lot? No? Change, believe it or not, the change in A is small. In fact, this is the situation when the change is the biggest. If he moves his hand at the same rate as the ball is moving, then this will make it have the maximum amplitude. This has the most effect, the most change in A. And there's a word in this in physics, and Ugo, when I write it down, you'll know exactly what I'm talking about, but maybe you've not thought of it this way before. Resonance? Yeah.
Use that mainly to determine the speed of sound.
Yes, yeah. Resonance, resonate. So what exactly am I saying here? Well, I'll give you another example to help you picture it. Okay, can I go down? So you know from your chemistry class with Lorraine, when you look at a solid object, what makes up this object? Atoms, isn't it? So you have all these atoms inside here, yeah? Now, have you done with Lorraine solid, liquid and gas? With Lorraine? Have you? Like, what are you doing in chemistry at the moment?
Polarities.
Okay. Well, I doesn't matter.
I think we know what solid, liquid and gas.
Yeah. All these atoms make up the table, okay? So for example, with water it's H2O, but you know all this from chemistry. The atoms make it up. Are these atoms moving or not moving, or what are they doing? Yeah, these atoms are moving, and as you said it here, they're vibrating. It means the atoms are moving like this, inside. Okay? So all of these atoms are moving. And in fact, what type of motion do you think it is? It's simple harmonic motion. These atoms are going like this, left, right, left, right, left, right, left, right, left, right. Okay? If I come along and then shake the table, if I can shake the table at the same frequency that these are moving at, I can make these atoms move more. Then, if atoms are moving a lot, you could then maybe break the bonds.
There is a video of the bridge, I saw.
That's the one, the bridge one, yeah. So there's the video of the bridge. So what's happening is, there's a hammer, isn't it? And the hammer is hitting the bridge. And you think, that hammer is not going to break the bridge, because it's a big bridge and a small hammer, yeah? Okay, the one I'm thinking of is this one. You have a big bridge and you have a hammer, and the hammer's hitting the bridge like this. But the frequency of the hammer is the same as the frequency of the atoms. So each time it hits the bridge, these atoms get a bigger amplitude.
Yeah. And that's why it's like it's not allowed some good marching, so understand.
Yes, that's the same reason there, yeah. So what will happen is, you keep hitting this, and all the atoms inside it start to shake more. And then after enough time, the bonds break, and then the table breaks, or the bridge breaks.
Yeah, that's like opera singers.
Yes, that's the other one, the opera singers. Do you know you see the person break the glass when they sing?
Yeah.
The reason for that is, here's the glass. So inside the glass are the little atoms, and they're moving with frequency. So for example, I'll just say the frequency, I don't know, is 10,000 hertz. Well, maybe, I don't know, 40,000, whatever. So they're moving really fast, aren't they? If this person that's singing, if they can sing at the same frequency, exactly the same, then when the sound hits the glass, it causes these to shake a lot. And if they shake enough, then it will break. Okay? So this is called resonance. The idea is, if you have the same frequency as this motion, and you force it at the same frequency, you make the amplitude bigger. That's the key idea here. Okay, what I'll do, I'll let you try these questions just for a few minutes, but then there's something I need to show you at the end for the next lesson. Yeah, so just for a few minutes, try, 5 minutes at least. the next page, the questions there.